Let's see how this goes. Awesome, I think we're live. Welcome back, everyone. Thank you for joining us for today's Low Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we are presenting interferometric measurement of the magnetization and spin of supermassive black holes by Daniel Palumbo. Daniel recently this year obtained his PhD from Harvard University. He got his bachelor in physics from MIT, and he's going to start his postdoc at the Black Hole Initiative as a fellow. Daniel, in my opinion, is one of the youngest rock stars in the EHT member. He's an expert in polarization, in images processing, and I'm very happy to have him here today. Remember, you can ask questions over email, through our YouTube channel or Twitter, and the questions will be read at the end of the talk. So without further ado, we will turn time over to Daniel. Thanks for joining us.
Great, thank you so much. So first of all, it is a huge pleasure to be here, and many thanks to Alejandro and the Law Physics program for inviting me to come talk about the stuff that I'm super excited to share. So let me try to share my screen here. Hopefully this works uneventfully. There we are. And this ought to be full screen. So perfect.
Perfect.
Excellent. So yeah, as Alejandro mentioned, I'm here to tell you about interferometric measurement of magnetization and spin of supermassive black holes. So I come to you from the Event Horizon Telescope, which is an extraordinary instrument and an extraordinary collaboration that set out a long time ago, really, sort of time has flown, to make the first images of supermassive black holes. And if you had asked me in 2016 or 2017 what the purpose of the EHT was, it would have been just that. It would have been just to produce these two images here. So on the left, this is a picture of Messier 87, which is the supermassive black hole, the heart of Messier 87, which is a giant elliptical galaxy. And on the right, this is a picture of our very own Galactic Center, supermassive black hole. And on the left, you see these little white tick marks. These white tick marks will be all over the place throughout this talk. And all that they mean is in a little patch of the images that I will be showing you around each little tick mark. That's showing you the total electric vector position angle in that little patch. So if you imagine light coming at you like a wave in that little bundle, that is the way that light is oscillating. It's the polarization of that light. And so given these two images, these are a massive achievement on the part of hundreds of people over decades. And yet a few of us on the theory end have the temerity, have the audacity to ask, what have we actually learned from these images? Are they just pretty pictures? Or have we gained an understanding of something deep? Or is there something missing? Or is there something more that we can learn from looking at these in a different light or looking at them over and over again? And so much of my work has been tackling theoretical understanding of images of these sources, and particularly polarization. So polarization results have been published for Messier 87. They are very physically rich, much physically richer than total intensity, which is what we refer to the image on the right as when you don't have this polarization information. But this is soon to be arriving for Sgr A, so stay tuned. And so just to outline some of the things that we've been able to infer so far. So these are existing conclusions from Event Horizon Telescope results, which set the scene for what I'll be discussing today. We've seen from our simulations, this is a statement rooted in general relativistic magnetohydrodynamical simulations, these GRMHD, which you'll hear me say a lot. You'll be very sick of hearing it. We infer that M87, Sgr A, have masses that are consistent with prior measurements. And the way we do this is we can run simulations of black hole accretion flows that we think are sensible for low luminosity active galactic nuclei, which we believe Messier 87 and Sgr A are. We can run these simulations in a essentially scale invariant way. We can fit the mass of the black hole, we can fit the density of plasma around the black hole in a way that's very, very efficient. And so we can perform a procedure where we change the mass and densities to fit the compact flux that we observe and to fit the angular size that we observe in EHD images. And when we do this procedure, we see masses that track. So that's a great first step in convincing ourselves that we're doing something right. That we can, when we simulate black holes to the best of our ability, we end up with masses that match measurements which make very different assumptions and fewer in many cases. When we look at our models, especially in polarization, when we put on our polarization goggles and look at the morphology and the strength of polarization in these sources, we see a preference for dynamically important magnetic fields in the accretion flow. And I will spend a great deal of time unpacking that statement, but just at first glance, you can look at those little tick marks around your image of a ring and draw some conclusions in comparison to simulations. And these tend to favor strong magnetic fields, which has sort of echoing ramifications for what we believe about these sources. And more generally, our models resemble actual black holes, but we know for a huge number of methodological reasons and physical reasons that our models aren't good enough. They're not just not perfect, we know there are massive missing pieces, limited by computation, limited by a lack of scalability, and I could spend a full hour just talking about all the things we don't believe about these models. Though I won't do that, it would be a very, very morose talk. And so we believe our results much more when simple, universal, physical arguments back up these detailed GRMHD comparisons. If we can write down simple, sort of causal arguments for why we might see certain things and convince ourselves that these might be general or get a sense of what is required to be able to make deep statements about these sources, we are much happier than when we have these huge, complicated black box simulations that are sometimes difficult to interpret and which have deep methodological limits. They're the best in the world, but the best in the world is still very difficult to make sense of sometimes. And so my work has been largely on building tools and future experiments that connect these messy astrophysical measurements to fundamental physical properties, rather than trying to avoid the messy astrophysics, allowing this astrophysics to illuminate the spacetime of these black holes to make the next generation of VLBI as physically exciting as possible. And in this light, I see the next holy grail to be spin, the spin of the black hole, the angular momentum hidden in the horizon. And so with that in mind, I think it's useful to consider why this matters at all. So spin is a very special property in the field of studying black holes because it is important both at the sort of messiest ends of the problem and the most elegant and fundamental. It's one of only a handful of parameters that fully describes astrophysical black holes and their spacetimes. Along with mass and spin, it basically describes the whole spacetime around the black hole, and with inclination, our whole viewing geometry with respect to it. So in a geometric sense, it's one of only 3 parameters we really care about. And in an astrophysical sense, it's deeply important to outflows, for example. We believe that the way these powerful jets that we see here in Messier 87 viewed in the optical, you can see this thin blue feature. It's a 100-year-old discovery that M87 contains this linear feature. We believe these jets, which are coming at us at near the speed of light, these are launched on thousands of light year scales, sometimes exceeding the scales of their host galaxies. We believe these are launched by the actual extraction of the rotational energy of the black hole through a process called the Blandford-Snag process. And so understanding the spin of a black hole lets us understand, is this process really going on? Is it possible to extract energy from a black hole in nature? I mean, we know it's theoretically possible, but is it happening? And is that what's powering these sources? And that, if so, that tells us something about feedback. When we look at models of stellar growth, it's impossible to get the right number for how many stars should be forming or growing in a galaxy without accounting for black hole feedback, without accounting for these jet outflows disrupting their environments. And so the history of structure formation in the cosmos is tied into the spin of the black hole. both through feedback and also through accretion and merger history. As you might imagine, if I have two black holes that are in some random misaligned angular momentum arrangement and they merge, I might end up with a lower angular momentum in the final supermassive black hole than if there was a single black hole coherently accreting material from a disk for eons and eons. And so theoretically, there's a great deal of interest in understanding spin. And observationally, it's very, very difficult to measure in low luminosity active galactic nuclei. At the moment, the only spin measurements of supermassive black holes that exist come from X-ray observations of very bright AGN, which are very much in the minority. The quiet, sort of boring majority of supermassive black holes that we believe to exist are rather quiet, rather dim. And the only tools that we have to think about them come from methods like those that I'll describe. And so there's great value in building out a toolkit for understanding the spin of these sources. So that is the motivation for trying to make any assumptions that are needed to get any handle at all on spin. And hopefully I will convince you that there is some hope by the end of this talk. So here's the outline for the work that I'll be reviewing today. First, I want to tell you about the polarization spirals that we see in M87 and simulations of M87, and how we've used those, and how paper 8 in the EHT series of publications on Messier 87 used some of my work to conclude that M87 is a magnetically arrested disk, or hosts a magnetically arrested disk, and a little bit about what that means for our ability to understand spin. Then I'll talk about some polarimetry of the photon ring. My understanding is that you've had some speakers here tell you about the photon ring before. Alejandro himself is, of course, an expert on the photon ring. And there are beautiful symmetries and really antisymmetries of polarization that reveal themselves in the photon ring, and which are very rich for detecting it and for understanding it. And so I'll be going through those as well. And lastly, I want to touch on black hole tomography, how we can use some of these polarization tools to understand not just our two favorite black holes, but potentially many more, perhaps an order of magnitude more in the near future and another order of magnitude in the farther future, depending on where telescopes get put over the next few years. So without further ado, I'll be reflecting on some of the EHT work on M87. To kick this off, it's useful to think about some zoology of accretion flows in low luminosity active galactic nuclei. We generally bin the accretion flows in these systems into two buckets. There are standard and normal evolving disks. So the standard normal evolution state is another way to say it, which for a long time, historically, was considered to be the default state for low luminosity accretion flows. They have weak magnetic fields that tend to go with the flow and have small scale turbulent structure, which are generally more disordered. But overall, if you imagine just pouring water into a kitchen sink and watching it spiral down the drain, the plasma itself is mostly coherently accreting towards the black hole. There's a sort of continuous inflow, and the magnetic field, because there is generally flux freezing in these systems, is just dragged along behind the plasma. And so on small scales, the field is disordered. Overall, you might expect a roughly toroidal structure in the magnetic field following the plasma. Whereas in magnetically arrested disks, which is what's being diagrammed here in Ramesh Narayan's sort of seminal paper, there are strong, dynamically important fields that pile up on the horizon itself. And so in this situation, you get very strong radial and vertical fields, which really can't be supported in just a coherent inflow picture. And most importantly, as you can sort of see in this cartoon, the magnetic pressure is sufficient that there is no actual steady state inflow solution. The material can't smoothly kitchen sink into the black hole because the gas pressure is being balanced by the magnetic pressure. And so you get this very clumpy accretion where blobs of plasma have to sort of sneak through the magnetic field in order to make their way to the black hole itself. And one very important prediction is that sane disks become magnetically arrested over time. If you have a sane system sitting out there in nature, coherently accreting from some torus of material in the center of a galaxy, one day it will be mad. Now that can be disrupted if the source of its gas changes, but all else equal, it will one day be mad. It will obtain stronger, more ordered magnetic fields, and this will tell us something about the outflow mechanisms and the history of its accretion if we go find magnetically arrested disks, or if we don't. Both are exciting. It tells you something about how coherent accretion has been in the recent history of the black hole, if you see that it's mad. And if you see that it's mad, you know something about the coherence of the magnetic fields very near the horizon, which are innately tied to this Blandford-Snag process, which is launching these powerful jets. In principle, both MADS and SANES launch these jets in slightly different powers because of the different magnetic field strengths, but these are all intricately tied. And so in the broad quest to understand what the magnetic fields are doing very near these supermassive black holes, as a minimum, we must understand whether we are looking at a mad or sane disk. And unfortunately, at the EHT resolution, total intensity is not sufficient to distinguish the accretion state or really anything else. So there are three sort of parameters to keep in mind if you have fixed your viewing inclination. So for Messier 87, we think we're looking at an accretion disk that is nearly face-on. We know this because when we look at the jet that's coming at us, we can look at the kinematics of material in the jet and conclude that it has an inclination of roughly 17 degrees from normal. So it's nearly pointing directly at us. And if we infer that the disk is similarly aligned, that means that we only need to determine the accretion state, the spin, and some properties of the electron distribution function, which is here encoded by this R high parameter. And the punchline of the theoretical analysis of the total intensity images of the EHT is that we can paint in any of these parameters that we want, but when we ray trace these fluid models, blur them to the resolution of our EHT, so we put on our blurry EHT goggles, these all look very similar. Once you get the direction of motion of the material right, they all have a Doppler brightness asymmetry on the bottom, and they all look basically identical. And so in a sense, this is a big triumph. We're great at making real images that look like real black holes, but it's very difficult to distinguish them. And so we need a new handle on the key differences between MADS and SANES. And these key differences are magnetic field geometries. And so here I've taken this diagram from Narayan et al., and I've tilted this so that it matches the M87 orientation. And I'm sort of painting a picture here of the kind of information we get because these sources at 230 gigahertz, where the EHT is observing, are generally dominated by synchrotron radiation. And so this synchrotron radiation is innately polarized perpendicularly to the magnetic field. So in this picture, each little field line that I can draw in my accretion flow is surrounded by a bath of particles moving in all directions. But if I isolate a single particle in this diagram from Rybakine-Leibman, you see that it has a helical trajectory around a magnetic field line, or just through a uniform magnetic field. So I can always find some local patch, which sort of permits this description. And so as a distant observer, I see polarization of radiation aligned with the axis of acceleration of individual particles, or the average of a sort of thermal bath, you might imagine. And so I can look at my image, and I will see a projection of the magnetic field onto my screen. Now, there are a lot of things that complicate this. It's not so simple in practice. There are propagation effects which twist the polarization of light as it passes through cold plasma, sort of Faraday rotation, Faraday conversion. And there's also lensing. We're looking at emission, which by and large is dominated by the inner fused Schwarzschild radii from the black hole. And so lensing is critically important to getting this right. It makes a huge difference to the appearance of polarization in our images. But at the sort of 0th order, we are just seeing the magnetic field in wherever is emitting projected onto our screen. So the hope then is that we can take simulations of these accretion flows. We can blur them to the sort of blurry resolution of the Event Horizon Telescope, look at polarization, which is telling us about the magnetic field, and looked for systematic quantitative differences in the polarization between magnetically arrested disks and standard and normal evolving disks. And so in this diagram from a paper I wrote with beloved colleagues George Wong and Ben Prather, we looked at a massive library of simulations produced by Charles Gammey's group in Illinois for use with EHD observations. And we looked at patterns of polarization. So fundamentally, we're looking at polarization morphology in the hope of telling apart MADs and SANEs. And remember, the picture here is that SANEs, we have a sort of smooth kitchen sink of accretion flow. And so we end up with magnetic fields, which are roughly circular when viewed top down. And synchrotron emission tells us that the polarization should be perpendicular to a circle. So a polarization field that is everywhere perpendicular to a circle appears roughly radial, like a starburst. And that's roughly what we see. The event horizon's over here, and we see with a huge Doppler asymmetry, lines spreading radially outward from the horizon. Whereas in this magnetically arrested disk, we see a spiral of polarization. There's more radial magnetic field contributing here. And so we wanted to quantify these differences and look at thousands of images to see if these really do shake out in practice. And we don't need to get into the weeds here, but the basic idea is that you can do what is effectively a Fourier transform around the azimuthal angle of the image to build a basis for different kinds of rotationally symmetric structure. So we called these modes the beta M modes. I regret using beta. It's very overused in plasma physics, and we should have called it anything else, but we're stuck with it. It's too frequently used now to go back. But the sort of key observation here is that one of these modes, the beta 2 mode, encodes rotationally symmetric structure. Now, other modes here also have sort of interesting interpretation, and there's lots of rich structure there. But for now, we're going to focus just on this m=2 coefficient. So this is a complex number, which is encoding rotational symmetry in EVPA, where the real part is radial or circular EVPA, and the imaginary part is handed spirals. And if you're familiar with sort of curl and divergence-free decomposition, sort of E and B modes, the beta 2 mode, you can think of as just a linear combination of E and B, sort of E plus IB. But the picture here is just that. This is a single number that we can report for an image, which is an integral of this rotationally symmetric structure over radius. So you need to define an image center, but it's telling you something about what this spiral looks like. The phase of this number is telling us the overall twist of the polarization in this very special, physically motivated basis. We are looking at a system that's roughly axisymmetric, and we're looking at it from the top down. We're looking down at a kitchen sink. We're looking down at a spinning top. And so that favors a basis like this one. And so if we take this massive library of simulations and we compute this beta 2 coefficient for all of them, we see some very interesting patterns. So on the left, this is the one that I personally find most exciting, and which has some deep ramifications that will sort of echo throughout the rest of this talk, which is that the phase of this coefficient, so here we're looking at it in the complex plane, but the phase tells us something about the spin of the black hole. So here in green, I have spin 0. In yellow, I have retrograde medium spin 1/2. Spin is a number between -1 and 1 for our purposes, where 1 is the absolute limit beyond which you have a naked singularity. And so, and blue here is in spin 0.5. And these tend to cluster on the lower left of the complex plane. So in morphological terms, these have more circular or spiraling polarization. Whereas when you crank up the spin to really high magnitudes, your polarization patterns become more and more radial. And you can ponder why that might be for a moment. I'll give you the answer shortly. But just sight unseen, with no physical understanding, this is already useful because this little gray circle is showing the constraints that we got on M87 from imaging. We get thousands of possible images explained by our data, but they all land in this little zone. And so this zone tells us a few things. One, it's probably not maximally spinning, or even very highly spinning. And two, it's probably not a sane. Why? Well, in this plot on the left, I'm showing everything all together binned by spin alone. So mads and sains and various electron distribution functions are all thrown in there together. But if I were to color this by sains, or by sane versus mad, you would see that virtually all standard and normal evolving disks are tucked away at the origin or sprayed out here in these black points, which are retrograde high spin. What this means is that in the sane paradigm, the magnetic fields are generally so disordered that the magnitude of this number is very small in a way that is easily distinguishable from magnetically arrested disks, except for certain special models. And so the utility of this observable in the EHT work is that we were able to knock out these last few standard normal evolving disks, which were otherwise very good at mimicking the polarization that we saw in M87. And so the decision that we believe M87 is mad hinged on the fact that we had some morphological constraint on the polarization. And that's what's shown in the plot on the right, is that the phase of this number disfavors this dark orange pile here. And this dark orange is these retrograde sains, where the large-scale accretion flow is going counterclockwise. The interior of the accretion flow is going clockwise because it's being frame dragged by the black hole. And those were otherwise very good at mimicking our images, except for by this token. Now, whenever a single discriminator is giving you your final answer, you should worry. And so this is something we're going to be confirming with future publications on new years of data. But it would be a little surprising for this conclusion to change significantly. I would say it would be very surprising. And so the more interesting takeaway from the plot on the left, and here's the answer to the riddle I've put to you, is that the spin is telling us something, or rather the polarization is telling us something about the spin by way of the spiral pattern in the image. In the image polarization. And this is the crucial takeaway of the entire talk. It informs the rest of everything I'll be telling you today. And so if you take one thing from this, may it be this slide. So we're looking at these magnetically arrested disks at a frequency where they're optically thin. And we see that the emission is peaked very near the horizon. It's in the ergosphere, which is a region where the frame dragging from a spinning black hole is most important. It's most significant. It's forcing material to rotate along with the black hole. And so the picture is that the spin of the black hole drags space-time around it. The space-time drags the plasma. It's setting the direction of rotation. The plasma drags its magnetic field behind it. Flux is frozen in. And these magnetic fields are revealed to us through polarization. And so if you believe the critical assumptions of this problem, which is that we're looking at a magnetically arrested disk, so far is a supported claim both for M87 and Sagittarius A star. So if you're looking at a MAD, if you believe you're optically thin, so you're seeing down to the horizon, then you can run this backwards. You look at polarization, you conclude something about the magnetic fields, which lets you conclude something about material rotation very near the event horizon, which lets you conclude something about the space-time, which tells you about the spin. So this causal trajectory and running the ability, the confidence to run it backwards gives you a great deal of information. And so believing those assumptions in the full generality of what this plasma might be doing is a major task for simulators. And my hope is that simulations which are vastly different in paradigm and character and resolution and assumptions and initialization conditions, all of these things, will harmonize, that they'll give holistically comparable answers. And so far they are. And there's many papers looking into this in different simulations. I've thrown a few of them on the bottom of the screen. And so far, this holds water. And it's very exciting because as long as it does, we can potentially extrapolate. We'll be getting into that in a bit. But for now, I want to digress for a moment to polarimetry of the photon ring. So you've possibly heard about this before, but I want to go through this once again, just to introduce this beautiful, beautiful feature of images of black holes. So it is the case that black holes lens light around them. And so if you have a disk of emitting material passing through the origin of your sort of black hole coordinate system, it is the case that a disk produces rings on the image. And the reason for this, you can sort of imagine in two ways. In the forwards picture, any point in space has an infinite number of light paths connecting to the observer, and these paths correspond to an increasing number of windings around the black hole. And so these windings, or we typically index by half orbits, are this number n. And so here on the left, in blue, you can see a trajectory which leaves an emitter, and here are observers at the top of the screen. This emitter releases a photon away from the observer, but it's lensed around and makes a single half orbit and comes and hits us in our eyeball, in our telescope. And so we call this an n=1 photon. It releases another photon towards us, which is half orbited once, half orbits again, and then comes and hits us in the eye. We call this n=2. It's made 2 half orbits. Now you can also imagine a backwards picture where a point on the observer image corresponds to a single photon path, which might intersect a plane around the black hole any number of times. So here we've made this problem for a single point on our image. No longer are there many trajectories. There's one unique trajectory. And you can imagine if I launch a photon with a very large impact parameter towards a black hole, it's not going to wind around it many times. It's very weakly lensed. And so in this example, if you look at the one launched at 10 angular gravitational radii at the top, it sort of zooms by, weakly bent, and it only hits the midplane once after making 0 half orbital windings. So this is an n=0 photon. Now, either way you think about it, you launch geodesics closer and closer to the critical curve, which is this feature on the image, which I'll show you in a moment in more detail. But either way you cut it, you can imagine that the closer photons are to the black hole, the more they will wind around. And this winding produces a very special image feature, which is that we see an infinite sum of lensed images when we look at optically thin accretion flows. That's the asterisk. It's that if these are optically thick, or even marginally optically thick, eventually they will wind enough that this light is absorbed. The trajectories become too long and they are too diminished. But in the optically thin picture, when we look at a full image, so on the left, this is all of the light we see, we are seeing a stack of a big, fuzzy, complicated direct image that's weakly lensed, plus a more strongly lensed n=1 image, which already looks like a very sharp ring. And as we increase n, as we increase the number of half orbital windings around the black hole, these images get exponentially sharper and exponentially dimmer around a critical curve, which is extremely well approximated by the n=2 image, and which is encoded just by the mass to distance ratio of the black hole, which scales the whole system in and out, the spin of the black hole, which warps the photon ring and warps the critical curve, and the inclination, which tilts and sort of vertically, or I guess along the projected spin axis, is also sort of squishing the curve and making it more asymmetric. And so having sensitivity to the photon ring is incredibly exciting for understanding the parameters of the black hole in a way that is very insensitive to the astrophysics. You can change a great deal about the accretion flow and its large-scale fuzzy structure while changing very little about the n=1 and n=2 images. It's also a good test of GR to see whether this thing even exists at all. Are these objects behaving as we expect black holes to behave? And it's worth worrying about, and I don't want to dwell on this because I don't want to get too much into interferometry here, but by and large, the Event Horizon Telescope observes Fourier transforms of images. And so if you look at the Fourier transforms of these two decomposed images, where I've taken the full image and broken it apart into the weakly lensed and strongly lensed n=0 and n=1 images, on the short baseline, so what you might see with a very small sort of micro EHT that wasn't very high resolution, we are just seeing a blob, and the majority of light in that blob is coming from the direct image. But as we go out to longer and longer baselines, we spread our telescopes apart, we are sensitive to finer and finer structure. These scales become separated, and the contributions to our signal from the direct and indirect image become more comparable. And so at the longest baselines we see at the HT, which start at 8 gigalambda, and as we go to higher frequencies, we'll push higher, we see roughly half of the signal we expect from simulations is coming from the photon ring. That doesn't mean it's easy to make strong claims about it, but it means that we darn well better be ready to think about it, because it might be about half of the light we're seeing. on our longest baselines, and even more as you go up to longer baselines. And so where this all enters the polarization picture, I can be motivated just by taking this diagram, and I want you all to think about this. Picture taking this diagram and flipping it upside down and looking from the underside. So when you do this procedure, a radial polarization pattern stays radial. A circular polarization pattern stays circular. But these handed spirals flip. If you see a right-handed spiral, when you look at it one way, it will appear left-handed when you flip it upside down. That is a B-mode antisymmetry, is one way to think about it, where you will see sort of twisting patterns flip in handedness. And so in this very silly sort of flat space construction, that corresponds roughly to what the n=1 image sees. The photon ring includes the image that would be seen from the underside as it is projected around the origin and loops back to hit you. And so you would expect that the photon ring, if the direct image looks like a beta-2 of, for example, -I, you'd expect that the n=1 ring has a beta-2 of I. Or if you can think of this just in terms of B-mode signs, if you wish. And so that's very exciting because that would be an intrinsic difference in the light that we see from direct and indirect images. So it turns out there's a lot of deep reasons for this. The first was and also a sort of recent history of papers looking into this. There's a wonderful paper by Mina Himwich, Michael Johnson, Alex Subsaska, and Andy Strominger, which found that the Penrose-Walker constant, which encodes polarization structure along sort of parallel transport, it's a conserved quantity of parallel transport, should complex conjugate across subimages in this high-n regime where everything behaves very nicely in Kerr, so in the space-time of spinning black holes. And there are a lot of assumptions that go into this. It assumes equatorial emission, single radius, but fundamentally, if you look near the critical curve, you will see a little dance done by polarization, where it'll jiggle as you move across adjacent subimages of increasing windings. Now, this is very tricky to get this high an n into this universal regime. It's very dim, it's very sharp. But even if you just look at the sort of n=1, like the simplest case in GRMHD simulations, there's a wonderful paper by Alejandro Jimenez-Rosales and collaborators in 2021, which found, without reference or really knowledge of this other theoretical work, that if you just look at simulation images, the photon ring region looks depolarized. And so here in this diagram from a paper of mine with George Wong, you see in total polarization that there are strange dark bands which tend to appear very near the photon ring, where the polarization suddenly plummets, specifically in magnetically arrested disks. And it turns out that this is coming from precisely the effect that we motivated with this flat space argument, and where the direct image might have one beautiful handed spiral going one way, and when you look in the indirect image, and it's a little hard to see because these ticks are pretty tiny, the spiral will be going the other way. This is super exciting because it is something intrinsic to look for. It's something special about the photon ring, which makes its radiation easily distinguishable from the direct image. It tells us that we're looking at fine structure that can't be coming from the direct image because there's no reason for the accretion flow to be producing stuff going that way if it's moving progradely. Now, the situation is more complicated if it's retrograde, because then you can get the wrong-handedness coming at very different image scales, and you need a little more subtlety. But as you might imagine, since these two images are overlaid, there is destructive interference within the image from the photon ring interfering with the direct image because their polarization is oppositely spiraling. And you can work this out analytically. This Penrose-Walker conjugation, which is sort of complicated, it's not something you have access to in observations, just reduces to a pure B-mode negation in the face-on zero-spin limit. It's very simple to work this out. And it's approximately true that this B-mode negation persists in spinning inclined black holes in the limit. And so this is a beautiful feature to look for, and it forms a tapestry with the rest of what I've been telling you in this talk, where the polarization in the direct image, the primary weakly lensed image, is telling us something about the dynamics of the plasma on the smallest scales, very near the event horizon where frame dragging reigns supreme, where as we spin our black hole up, So here in the center, we have a short shield black hole with a very weak spin. And as we move to the left, we are increasing our spin in magnitude, but orienting it oppositely to the right, to the large-scale accretion flow. And on the right, we're spinning up our black hole aligned with the large-scale accretion flow. In both cases, because we're looking so close to the horizon, where the black hole is forcing all of the material to rotate with it, we see the same thing. Higher spin equals more radial polarization because of that causal chain I mentioned earlier, where the black hole sets the tune for the plasma drags the magnetic field, and we see polarization perpendicular to that magnetic field. When we look at the photon rings, we see the handedness of these spirals flip, which is something to look for, and I'll give a teaser in a moment for that this might actually be very elegantly observable in the Fourier domain, but this is something to look for in images as a depolarization. There is destructive interference between the direct and indirect images of accretion flows around low luminosity AGN. It's a generic property as long as you're optically thin and you're magnetically arrested. And one last exciting little tidbit is that the retrograde flows reverse handedness in this polarization signature on large radii, where it's too dim for the EHT to see it, but future arrays with denser coverage and better dynamic range can look for a flip. And you can see this on the left-hand side of the top left image, where the spiral is going one way and then turns around. This is a generic property of all retrograde magnetically arrested disks, and it's a signature that something is changing direction, that frame dragging is present. It would be very exciting to see this. And at the bottom, I just want to highlight that there's a whole cottage industry of fellow obsessives who care about polarization in these flows who have been developing this reasoning. And yeah, just as a teaser, there's a very elegant Fourier representation and a potential single baseline VLBI experiment that you can do to look for this that might be relevant very soon. So I just want to use my last few minutes to tease something I find very exciting, which basically is arguing that you can assume a great deal and learn a great deal, sort of in proportion to how much you're willing to assume about the black holes that fill our local universe. So if you assume all AGN are magnetically arrested, which you can argue from the fact that we've seen two black holes, they both look magnetically arrested, and also from the fact that all standard normal evolving disks eventually become magnetically arrested, you get access to all of this machinery that I've been outlining. And so for a given population, you assume a bunch of things about mass distributions and accretion rates, which are mostly phenomenological and empirical. You can always find a frequency where they'll be optically thin. And for the roughly half of these that will be weakly inclined enough that all of this machinery applies, where we get this natural basis for thinking about this problem, where we're looking roughly downward at a rotating system, then we can apply all of our reasoning. And so you can argue that by assuming a particular observing frequency and some empirical population properties, you can estimate what you can see, what you can fit, what you can analyze with a particular array. And so here, I especially want to shout out my wonderful colleague, Dom Pesci, who has done some wonderful, wonderful work studying black hole demography using these techniques and others for measuring both masses and spins in marginally resolved sources. And so he's done some very detailed simulations here. This is just a very simple picture argument where as you blur out one of these simulations, where, as a reminder, as we increase spin, the polarization pattern becomes more and more radial. As you blur and more weakly resolve the source, this polarization pattern persists much longer than the shadow. You lose access to the sort of image claim that we're looking at a black hole much faster than you lose access to this polarization information. Though both are eventually destroyed if you don't resolve the source. And in detail, you can use an example array, one instance of a potential future next generation event horizon telescope, which has very dense coverage and much higher signal to noise ratio, to look at what you can access in a black hole that is less than 10 microarc seconds on the sky. And I want to highlight how small this is. The EHT images are about 50-ish microarc seconds in angular size. This is about 2 or maybe 3 resolution elements. It's about 3 grapefruits across on the moon. This is less than half of a pixel. This is you can imagine this is a super resolved roughly pixel scale measurement for the EHT. And so the intuition here for why the NGEHT within this dashed green band on the right, in this sampling space of all of the black holes and their expected masses that we know of in our local universe, supermassive black holes, I should say, we are able to access this spiral polarization pattern information even when we can't access the shadow. And the intuition is just that we get roughly one spiral per pixel. And so for all of these supermassive black holes, which are about 1 pixel in the sky, we can sample this property over and over and over again. And if we see coherent polarization structure over and over, that's evidence for madness from a magnetically arrested disk. It's also evidence for madness of the observer, but we're going to do it anyway if we can. And if we see this coherent pattern with a smooth average over time, that's telling us about the spin. And so that could be 10 and potentially even 100, depending on how the uncertainties on these sort of phenomenological patterns or properties slide around, where right now we have 0. No low luminosity AGN spins have trustworthy measurements. And so this would be groundbreaking for understanding the accretion and merger history of our local universe. I find this very exciting. And as you might imagine, if you expand into space, these numbers get much better. So I will conclude. I think I'm at 45 minutes, at least by my own little watch. So just to say, optically thin accretion flows reveal a great wealth of information in polarization. And M87 and Sagittarius A star, which we will be studying for the rest of our lives with any luck, will serve as a testing ground for our phenomenological understanding of these sources, our qualitative belief that we're doing anything right in our GRMHD simulations. And as our simulations improve, there will be a meditation, a question of faith and trust in, are these representing nature at any level that we are willing to extrapolate to sources that we cannot image, where we just get a single pixel, an integrated view. And if we do believe it, and this, I really do think that the crux of this debate will be in the next few years as these simulations are improving at an alarming rate, we will be expanding, in tandem, our arrays themselves. And so as our simulations improve, our ability to just stare at these sources and look at all of their rich structure and look at how wrong we are, measure ideally how wrong we are, will also improve. And so the way I see it is, we have one very special tool, a sharp probe that is very sensitive both to astrophysical effects and radiative transfer effects, but also very sensitive to the structures of the space-time. It will be critical to have this polarization handle on the physics of the system. And next-gen VLBI, and how exciting it is to the physicists in the room, you all, the many physicists listening to this, that relies sensitively on polarization. I see it as a uniquely powerful tool for learning anything deep from these images, and these images will be getting better and better. And so I will end with a teaser that I really do think the first hints of the photon ring, the first hints of light orbiting matter may be accessible in the near future with 345 gigahertz observations by the next generation Event Horizon telescope. If this story hangs true, that magnetically arrested accretion is pervasive and indeed present in the Galactic Center. And so I personally I feel very lucky to be alive to see this. And so for now, I will conclude. And thank you so much for listening.
Awesome. Thank you very much, Daniel, for this very, very nice talk. Let me see if I find questions over YouTube or here. Let me start with one question by myself. So do you have an idea of a forecast of the spin we might be able to measure, like how large the bound might be in the best scenario case or something like that? Can you just...
I totally get what you're saying. So I think there's sort of two steps to this. The first step is, if you assume that all you get is this sort of blurry image integrated measure, and you look at a source over and over and over again, if you believe you have a sense of the electron distribution function, then these distributions where you see this wild variation in the polarimetric structure actually shrink a great deal. The main limitation there is actually a radial uncertainty and not a sort of argument uncertainty here, coming from how depolarized the source is. And unfortunately, that's the part of our GRMHD and our ray tracing that we believe least. And so the thing I'm very comfortable stating is that we will be able to draw a line in the sand between a spin of, say, 0.8 and lower and 0.8 and higher, where as you get to very high spins, you see very qualitatively different accretion, whereas lower spins, because the effective spin is very nonlinear, are very difficult to tell apart and much more sensitive to different thermodynamics in the flow. That alone is still very exciting, because whether or not low luminosity AGN are maximally spinning is like a deep unknown.
Yeah, thank you. And then just to clarify, so this applies to both Sagittarius A star and M87. It's roughly the same picture type of like.
So that is a major caveat, and it's something that is an unknown for our era right now. Is why is it that when we look at Sag A star, we see something that looks like a gently inclined black hole? Why does its inclination look like it might be 30 or 40 degrees when we are just sitting in some random part of a spiral arm in a disk with a black hole that you would guess would be pointing out normal to the plane? And it might be a question of coincidence. It's something where we are not the first to see this indication. You know, there's these gravity results where they see roughly face-on looking hotspots. Very curious. Time will tell.
Thank you. Let me see. Does someone here of the coordinators have a question? Let me go to YouTube in the meantime. Okay, someone is asking me here, how do you know like roughly half of the photons are coming from the photon ring? The first, I guess it's the first photon ring. What they mean.
Yeah, so I should clarify.
And if I might ask also a follow-up, because this sort of depends on the source, right? Like if you change your model here, this plot that you have on the right might change.
Yeah,
I would expect it will.
Let me back up and say I went through this very fast. Far fewer than half of your photons are coming from the photon ring. It is the case that when you look at large spatial frequencies, you are selecting structures in your image which are very fine scale. And so it's more than half of our signal at large spatial frequencies is coming from the photon ring. The actual fraction of light coming from the photon ring, you can look at the ratio between this blue curve at UV distance 0 and the red curve at UV distance 0. So in this case, it's more like 20%. Now, yes, this is also super model dependent. It is the case that magnetically arrested disks tend to have brighter photon rings. There are deep reasons for this that I don't want to get into, but a lot of it is actually the fact that our emission is not isotropic. And so you get beneficial Doppler boosting into the photon ring and beneficial K cross B sort of synchrotron anisotropy effects that tend to slightly amplify the photon ring. But even in our most optimistic case, like you pick the highest flux fraction of the photon ring simulation, that's only 20% at 230 gigahertz. And all I'll comment on is that as you go to higher frequencies and it becomes more optically thin, the source gets dimmer, but the relative flux in the photon ring gets higher. And so this whole procedure gets easier as you go to higher frequencies.
Thank you. There is a minor delay, so there might be a follow-up or something.
No, that's fine. Yeah.
Okay. Any other question? Let me see here. Okay, I have another one. So I know nothing about scattering, and I would like to know, should we be worried about this type of observables because scattering does something? What I mean is like the polarization leaves, but then something happens between the source and us. Is that a real concern?
So there are two big concerns for trying to apply this to Sagittarius A star that we don't have to worry about for Messier 87. So for Messier 87, you can imagine that in between the image and us, so in between the source and us, there is some Faraday screen which might coherently rotate all of our polarization. We can usually estimate this, but it's generally fairly low for M87, whereas for Sag A star, there's much more stuff between us and the galactic center because we're sitting in the disk with it. And so this adds both much bigger Faraday effects and much stronger scattering to the point that we actually have to worry about scattering it at all. The good news is scattering can be broken down into two effects, one of which is a sort of diffractive blurring effect, which you can actually kind of get around with clever observational tricks. There's also a refractive effect, which is much deadlier, I would say, to this observable. And I have a student, Caitlin Chevelle, who's working on this very problem of at 230 gigahertz, it's likely that this is not possible for Sgr A, but at 345, there's a critical turning point that makes it just accessible from the Earth's surface. On new long baselines don't really exist yet, but there are places you could put telescopes that would make it just possible to get around the scattering. So it's very close, it's marginal, it's in the regime where if our simulations are 10% wrong, it's not possible. But given what we currently believe as our best bet, we might have some hope, which is very exciting.
Thank you. But then why do you think the first evidence might come from Sagittarius A star and not from M87, if in some sense might be easier?
Yeah, so the trick here is that M87 is smaller on the sky. And so there is a turning point that you can expect in these simulations where the photon ring becomes dominant in the polarization on long baselines. And for M87, that turning point is 15 gigalambda. And unfortunately, that is just not accessible from the Earth's surface until you get to 460 gigahertz. And I don't think anyone's planning to build anything there anytime soon. If the Greenland telescope is moved to the summit and gets a new receiver that I think is not planned yet, but it might be, I will change my tune.
Okay, thank you. Okay, I don't see more questions. Any questions from the coordinators here?
Yeah, I have a question for
yes.
So very nice the webinar, Daniel. Congratulations. But I was wondering, is any other correlation that you can get from other type of wavelengths, like for instance X-rays, or like to complement the analysis, like a normalization of the amount of photon flux that could produce? I mean, I'm wondering because usually kind of for the case of the Milky Way, you have that sometimes the protons that are in these gas clouds around the black hole produce pions, and these pions produce X-rays because of the decay of the pions. So I don't know if these photons could generate this half winding N2 and 3, but in another much higher energy level.
Yeah, so I guess there's a few sort of complications there. One is that when we look at Sagittarius A star, we don't always see a correlation between sort of radio flares and X-ray flares and other sort of infrared flares. So we don't always know we're looking at the same structures. And so even if we were seeing the same lensing effect, it's not clear that we could associate them with the same emission regions. But in principle, if you think that the accretion flow or just the material around the black hole is optically thin to the emission you're excited about, then you can always argue that there will be this sort of lensing echo. And I think the problem is that at those higher and higher frequencies, or at those sort of ultra high frequencies, you don't expect optically thin transport from wherever this emission is coming from to where you would see it. And also, I guess separately, there's not always enough flux or enough really high temperature electrons or high density to generate enough of this to see this in an expectable way. But I want to sort of acknowledge that there are some people working on sort of untraditional photon ring-esque projects, looking for lensing, for example, from some masers, that kind of thing, where you don't need to look at the high-end images from stuff in the accretion flow. You might expect temporal signatures from stuff from way out there as long as you're optically thin. So I want to leave this on the table. It's just very tricky to observe.
Okay, thank you.
Awesome. Wonderful. Thank you. I think we are past the hour, just on time. Daniel, thank you very much for this lovely webinar. People might contact you and look your data on your webpage, and if there are more questions. So thank you all, and thank you, Daniel. And I hope to see everybody in the next webinar.
Thank you so much. Yeah, please feel free to email me with questions. I'm always happy to chat.
Awesome. Okay. Bye-bye.
Great. Thank you. Bye-bye.